Okay, this video is on goal 2 of differential equations. Goal 2 is drawing a slope field from a differential equation. The slope field, remember, gives the answer, gives a sketch of the graph of the answer to the differential equation. We've done slope fields before, but we didn't do them for differential equations that had both x's and y's in them. We just did them for equations that had x's. So when we did them with x's, whatever we found for the slope, we basically just went up and down with the same slope. Now, this differential equation says the derivative of whatever function we want, which is the slope is based on x and y. So when we go to draw our slope field, we have to consider x and y, because basically the slope of the function, we're looking for a function y equals f of x. This thing says the slopes are the x coordinate plus the y coordinate. So if I add the x coordinate to the y coordinate, it'll give me the slope of the original function. I'll be able to get a picture for what the original function or relation looks like. All right. So the way you do this is literally to find the slope at each spot. What they will do on the AP exam is usually they won't give you this grid necessarily, but they'll give you these dots. So notice that there's 1, 2, 3, 4, 5 by 1, 2, 3, 4. There are 20 dots on here. They normally don't even make you do that many. But basically where the dots are where you want to make the slopes. I'll show you a real AP problem at the end so you can see an example of how they would really ask it. But if you need to do a slope field, basically on each one of these dots, I need to put a slope. And the slope I'm going to calculate by using the x and y coordinate according to this derivative. All right. Just be reminded that slopes in general, let's see if I have something, should have got an extra piece of paper. I'll just do it on the side here. Remember, you can sketch the slopes. A zero slope is flat. A slope of 1 is at 45 degrees. So if you want to do a slope between 0 and 1, something like a half or a quarter, they'll be not quite at 45. So this is slope of 0, this is slope of 1. Slope steeper than 1, try to make them like look pretty steep, like up 2 over 1, or if it was super steep, you'd make it even more vertical. If you do negative slopes, a slope of negative 1 would be downward at a 45 degree angle. Fractions like negative a half might look like that, and then negative 2 or steeper would look something like that. So when I calculate these slopes using this equation, I'm going to graph them according to this. I'm just going to do my best pitch. All right. On the AP exam, it doesn't have to be an exact slope. It just needs to look like it's pretty close to what it's supposed to be. And once again, I'll show you a real example at the end. All right. So in order to get the slope field, I'm going to need one of these directions on each dot here. Basically, I have every point that we're going to be looking at. They have these dots on integer points. So basically, I'll use the integer points to calculate what the slope looks like. Now, I realize the slope field, I'm only going to be doing at these dots. You could do it in between and anywhere. So the real slope field has like infinite resolution. But since I'm not required to do it at every infinite spot, that would be ridiculous. They're only having me do it at select spots. So the select spots are integer points. As you can see, like this spot is 1, 1. So I'm going to fill in this table to figure out what the slopes are. According to the differential equation, the slope at negative 2, negative 1 should be x plus y. So basically, I just need to do negative 2 plus negative 1. So to calculate what the slope is, I need to do this equation, negative 2 plus negative 1. Negative 2 plus negative 1 is negative 3. In this, for the next point, negative 2, 0, well, negative 2, 0 would be negative 2 plus 0, so x plus y. The slope at that spot is negative 2 plus 0, which is negative 2. Now, I'm not going to keep showing these because it would take forever to write. Basically, according to this equation, the way I get the slope of the function is just to add the x to the y. So I'm going to keep doing that. At negative 2, 1, I would do negative 2 plus 1, which is negative 1. Negative 2 plus 2 is 0. Now it goes over the negative ones. Negative 1 plus negative 1 is negative 2. Negative 1 plus 0 is negative 1. Negative 1 plus 1 is 0. Negative 1 plus 2 is 1. 0 plus negative 1 is negative 1. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 1 plus negative 1 is 0. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus negative 1 is 1. 2 plus 0 is 2. 2 plus 1 is 3. And finally, 2 plus 2 is 4. Now that I have a slope for each one of those dots, every dot I calculated a slope over here. I'm going to sketch the slope. That's what it means to make a slope field. And the slope field traces out what the original function would look like. This thing's antiderivative, whatever it is. We actually don't know how to solve this. This is not separable. But if we did know how to solve it, we would get some equation or relation that would have a graph that sort of follows the slopes I'm going to put on here. So let's start putting the slope field on. Basically follows the pattern that does all the negative 2 points at x and all the negative 1 points at x. So basically it's going to scan across here. So I'll start at negative 2, negative 1, which is down here. They say the slope of this is negative 3. So I'm going to do my best to, and since I have these boxes on here, I could kind of get the pitch. Negative 3 would be down 3 over 1. I just need to put a slope on that spot. That slope's about negative 3. At negative 2, 0, the slope is negative 2. The negative 2 is down 2 over 1, so the slope, there's down 2 over 1. I'll just sketch it in. It doesn't have to be huge. It just has to be around that spot. There's a slope of negative 2. At the spot negative 2, 1, the slope is negative 1. Well, negative 1 goes at a 45-degree angle. And then negative 2, 2 has a slope of 0. A slope of 0 is flat. All right, so there's the beginning of my slope field. Now I have to go do negative 1, negative 1. That has a slope of negative 2. Once again, I'll do my best sketch. Negative 1, 0 has a slope of negative 1, 45 degrees downward. Negative 1, 1 has a slope of 0. And negative 1, 2 has a slope of 1 positive, so that's going up that way. Continuing, 0, negative 1 has a slope of negative 1. 0, 0 has a slope of 0. 0, 1 has a slope of 1. And 0, 2 has a slope positive 2. So once again, I'm going to use the boxes here to do my best to sketch in what looks like a positive 2 slope. To finish this off, I'm going to do the ones here. 1, negative 1 is slope of 0. 1, 0 is a slope of 1. 1, 1 is a slope of 2. 1, 2 is a slope of 3, so that's a bit steeper than before. Then finally, the row of 2s. 2, negative 1 had a slope of 1. Next one's a slope of 2. Next one's a slope of 3. And then the next one's a slope of 4, so I'm going to do my best to make it look as steep as possible. All right, so this is the slope field. This represents a graph, or if you had some more detail, you'd see it a little better. Notice it, like with other slope fields, it kind of flows like a river. Like if you were here, you'd sort of follow the slope fields that way. If you were here, you'd follow the slope field off the graph. Basically, even though we haven't solved this differential equation, and this one, like I said, we can't solve with what we know because this is not a separable equation. Despite the fact that we don't know what the solution is, we have a graph of the solution. In fact, we have a graph of the family of solutions because basically there's lots of different answers and they all would fit on here. They'd sort of flow with the lines that I've put on for the slope field. This document is posted with this lesson. So I'll leave some of these other ones for you to try. I'll start this, but I won't finish it, and then you can see if you can get the other ones. So if I were to try the second one, this one I could solve because this one is a separable equation. I could divide over the y and move over the dx and actually get what the solution is for this. But if I just want a picture of what the solution is, I can just do the slope field stuff. Now notice this time the slope is the x-coordinate times the y-coordinate. So if I want the slopes, I can just do x times y. I'll do the -2s and -1s and then stop, and you can try it and do the rest. So -2 times -1, because basically it says do x times y. So I need to do -2 times -1, which gives me 2. -2 times 0 would give me 0. -2 times 1 is -2, and -2 times 2 is -4. -1 times -1 is 1. -1 times 0 is 0. -1 times 1 is -1. And -1 times 2 is -2. Now, I'm not going to finish it off. You can do that, but I will at least graph these. So if I want to then start sketching what the slope field looks like, I'm going to take -2, -1, which is the point here, and put the slope of 2 on it. So remember, 2's kind of steep in the positive direction. The next one's 0. Next one's -2. The next one's -4. So I'm going to try to make that look extra steep in the negative direction. So there's one part of my slope field. I'll do the next couple. -1, -1 is 1. Once again, I get 0. Then I get -1. Then I get -2. And you would continue doing this. One thing to note is if you get things that are undefined, I said I wouldn't go on, but I guess I better at least talk about if they're undefined. I'm not going to continue doing them, but in the next one, you might get division by 0. If you divide by 0, remember that's undefined, but as a slope, that would be vertical. So in this little diagram here of all the slopes, if you do get something that's undefined, that's essentially infinite. You'd get that by doing like a number over 0. Anything that comes out undefined slope, put a vertical line on the dot. All right, so these two examples don't have that, but this one would, because there's a bunch of spots where you're going to get x to be 0. And if x is 0, it'll come out undefined like this box. So at -1, 0 on this graph, I would put a vertical line for it being undefined. All right. This is the basic idea of how you make a slope field. It's not really that difficult, so long as you know how to put your pitches on correctly. And remember, what this is giving you is, instead of solving this equation, it's just giving me a sketch of what the graphical solutions would look like. Now, there's lots of different solutions, because I could kind of follow this little river of lines in all kinds of different places. I'll demonstrate in a moment, well, maybe a couple moments, how you would put on a particular solution to a differential equation if they ask. Remember, if they want a particular solution, they have to give you initial condition. They didn't give me any initial conditions here. They just want the whole family of solutions. This makes a graph of the family of solutions, and I'm starting to make graphs of the family of solutions to this thing. Let me show you another example. Sometimes they kind of go backwards. Instead of making you come up with the slope field, they may want to know which slope field goes with a particular differential equation. You can answer these similar to what I was doing before. It's basically two tactics. Number one, if you have something simple like this, if dy dx is sine x, it means the original function, this is the derivative of the function you're looking for. If you happen to know the antiderivative of this, so the original function y, would be negative cosine x. If you happen to know the actual solution to this, because I know if the derivative of sine x, the function has to be negative cosine x, you would then look for a function that looks like this. So this is matching. There are 4 graphs and 4 differential equations. Which one goes with which? Well, since this thing's antiderivative is negative cosine, this graph seems to have the pattern of negative cosine. If you're looking to solve them using the method I did before, because x minus y, you can't just take this thing's antiderivative very easily because it's a mix of x and y. So the problem is if you try to do the antiderivative with respect to x, you don't really know what to do with this thing. Now, you could try to solve it as a differential equation, but once again, this is actually not a separable equation. So this is actually not going to be solvable by you with the methods that I taught in the last video. And you wouldn't know how to solve something like this without a much more advanced course. But you can still get the slope field for it, because basically you're looking for the selection where the x-coordinate minus the y-coordinate would be the slope. So if I take a look at, say I think the answer to this is A, I'm going to look at the x and y coordinate and see if the slope comes out right. So pick an easy spot. So I'll pick 0, 0. If this were the answer, that spot 0, 0 should have a slope of 0, because 0 minus 0 would give me slope of 0. Notice here, the x and y coordinate are 0, but the slope doesn't come out as 0. Now, in B, the slope comes out as 0, and so does it do so in D. So I would maybe want to check another spot to be sure. I would want to take a spot that kind of looks different. So these two have flat spots at 0, but notice near the bottom here, this one's pretty steep and this one's flat. So I would see which one of these fits. Well, if I go to this one, say I have, say this is a spot 0, -2. Well, if the spot 0, -2, 0 minus -2 is 4, and that's not very steep. Notice here, 0 minus -2 is 4, and that looks steep enough to be a slope of 4. So the solution to 8, which one of these is its picture, D is. So you can check it that way. Another trick that helps to solve these is if you notice only one variable is in the problem. So this differential equation here, number 9, notice it's 2 minus y. It only changes with the y coordinate. When that happens, the answer to this one is actually A. You'll notice as the y coordinate changes, as you go up with y, everything across the way looks the same. So as you change x, nothing happens. But as you change y, the pitches change. That's because if we do 2 minus y, well, 2 minus 0 is 2, 2 minus 1 is 1, 2 minus 2 is 0. So you'll notice that if it's only in terms of one variable, you'll get sort of a repeat in one direction and a change in the other direction. Here's the reverse. This one I could solve in two different ways. I could do the antiderivative of this. The antiderivative with respect to x would be 1/2 x squared. So I'm looking for a parabolic one. That's the answer. But also notice that the slopes only depend on x. So as the x changes, the slopes change. But as the y changes, nothing happens. All right, so those are some different tricks to try to identify which one of these goes with each one of these. All right, so an AP question could always ask, give you one of these, have you figure out what the slope field is, or give you the slope field and ask what the differential equation that goes with it is. The standard way would be to do like I did it at number 8, is just to check some points until you only get one that works. But there's some other tricks too that work. So, whatever you understand or whatever you can do, the more you know, the better. All right. One last thing from this packet is to contrast another question. The other ones wanted me to match a differential equation with its slope field. This one wants the actual solution. So what you should know about this is now they're not giving me dy, dx's. They're not giving me the differential equations. They just want to know which one of these could be the solution to the differential equation. So they didn't give me the differential equation. There's dy dx equals something, something, something or other. But what we know about the slope field is the solution to whatever this is, which they didn't give us. The solution is some function. So basically, we're looking at the functions, family of functions here with their slopes sort of drawn. So these things are tracing out the solution. So I just need to figure out which one of these answer functions has a graph that sort of looks like these. Now, if I sort of trace one of them, say I start following the river here, say I start here and sort of followed what was happening, I'd follow these slope lines. The graph sort of looks like this. Now, the solution, so whatever y equals f of x is, the solution to this differential equation, this is a picture of it. So these graphs, if I know what they look like, some of them, well, basically 4 of them can't be the answer. X squared looks like a parabola. It doesn't have this kind of shape to it. So this is not the answer. E to the x starts off flat and then goes up. That's not what this looks like. E to the negative x is a little trickier, but remember, if you throw a negative on the inside of the function, it does a y-axis reflection. E to the negative x just goes the other way. This is the same as 1 over e to the x. It just flips the function around. So once again, not this picture. Y equals cosine x. Well, this is certainly not cosine x. Cosine x would be squiggling back and forth. So cosine x looks something like this, but we don't have that. Finally, the last one, if you know your graphs really well, natural log of x does have this kind of shape. Comes up, it's an asymptote to the y-axis, and that starts to not flatten out, but it slows down in its growth. So notice this has the proper shape. So which one of these is the answer to the differential equation that they never even gave you? The slope field matches this function. So be careful the difference between if they give you the differential equations and want you to match the slope field versus if they want you to match a slope field to its answer. Basically, the slope field will look like the answer equation. All right? Let's look at a couple other things. All right, so this is a warm-up I would have given in class. I basically wanted to illustrate some stuff on it since we're not going to be in class and I'm not going to be able to give it to you. It's still worth looking at. I'm going to do two things with this warm-up here. First, I'll solve it, but then I'm going to just show something else because these graphs are pretty detailed. Instead of having just a few dots on them, they have a very detailed set of slopes. So they'll help me show the idea of being able to graph one for a particular solution. Now, just to go over again, this is a real AP question. Which of the following could be a slope field for the differential equation dy dx equals x squared plus y? I'm basically looking for which one that has slopes that matches this. That basically, if I take the x coordinate, square it, and add y to it, that I will get the pitch to be correct. Now, there's lots and lots and lots of things to check. I would try to go maybe to a corner or to the middle or something, to an easy spot, and try to eliminate some of them. So for example, say I go to the top right corner, 2, 2. I should be able to hopefully eliminate at least one of them, because if I put in 2, 2 squared is 4, plus 2 gives me 6. So 2, 2 gives me 6. I would need something with a pretty steep slope. Now, maybe not the best spot to pick because that has a steep slope, that has a steep slope, and that has a steep slope. But this has a negative slope, so at least this one's out. So this one's not the answer. Maybe I should pick another spot. Maybe I'll pick the other corner here because this corner, this one's flat, this one's kind of steep, this one's really steep. So if I go to the other corner, negative 2, 2, negative 2 squared is 4. I'm still adding 2 because it's a positive 2 for the y. So negative 2 squared is 4, plus 2 is 6. I'm still getting the same 6. This doesn't have the slope of 6. This doesn't quite look steep enough. I'm going to rule it out, but I'll check it just in case. I mean, it looks like more of a slope of 1. This seems to have the really steep slope. So notice by checking just 2 spots, I was able to eliminate it down to D. Now, if you are a little worried that both of these are kind of positive and steep, I could try one more spot. Negative 2, 0 gives it away, because if I try negative 2, 0, this should come out, negative 2 squared is 4, plus 0 would be 4. This should be positive right here. It's not. Notice it is positive here. So D is the answer. And checking 2 or 3 spots is usually enough to determine which one's your answer. Now, the other thing I want to show on these is, because they're nice and densely packed, sometimes they have you sketch a solution on them. So if you want to sketch a solution, they would need to give you some initial conditions. So ignore the problem now. I finished solving this. I'm going to give another example. So say they gave you an initial condition. They might say sketch the solution at, and they'll give you a point. So say I use the point 0, 1. If they want a particular solution, remember a differential equation usually has the plus c in it, and it'll have a family of solutions. If you want a particular solution, just go to the spot 0, 1. So like say I want the particular solution, I'll do it for each one of them. If this were my slope field and they said draw the particular solution at 0, 1, I'd start at 0, 1, and I would just sketch in a graph that follows these slopes. So that's what the solution curve would be at 0, 1 for this one. At this one, the solution curve at 0, 1 would look something like this. And just do your best to follow the slopes. So that's what this would look like. This one at 0, 1 would kind of go up this way and then sort of curve like that. It's a little weird. It looks similar to this one. And then this one at 0, 1 sort of follows along here and follows along here and makes that kind of shape. Now, there's a family of functions. So if they asked me a different spot, let me go with, let's look at 1, 0 instead. So let me also make them for 1, 0. If I went to 1, 0, you sometimes get different looking things. So at 1, 0, the function would now be over here. And it would kind of follow and almost bump into the other one. So there's the solution at 1, 0. This one's solution at 1, 0 would actually be very, very, it looks almost exactly the same because this one almost bumps into it. So they're almost the same. This one at 0, 1 looks completely different because it goes over here and kind of follows down here. So the solution at 1, 0 looks very different from the solution at 0, 1, even though they're part of the same family of functions. And then this one's solution at 0, 1 would look something like this. So just kind of, doesn't want to, that's my best guess. All right, so long as they're close. So if someone asks you to sketch a particular solution, the slope field is sketching out all of the solutions for the entire family of functions that answer this differential equation. Usually it's something with a plus c in it, or a c somewhere, like that one I solved in the last video. I think it was like 1 over cx plus 1 or something like that. So basically these trace out the entire family of functions. If you want a particular member, just go to the spot and then follow it as if it's like I said, like a flowing river or a current or something, and just draw in your closest representation of what the function would look like. All right. This video is getting a bit long, so I'm going to stop this one. And in the next video, I'm going to show a problem that I really wanted to show you before that was multiple choice type, just in case they somehow modify it and ask it on the AP exam. And I want to show you an actual differential equations problem from an AP exam. So I'm going to stop this. Next video will have those two things, and that should be enough to then do the next assignment. I will have a PDF up of, not this warm-up, but of this document that I was working with before. Hopefully you can print it out, or if not, look at it. It's pretty long. It's 8 pages, but most of it is just the pictures take up a lot of space. So like this page has like 6 graphs. There's a page that has, I don't know where it went. One of the pages has like 1 or 2 problems on it. This one's a little more involved. So it's kind of long, but once again, there's only a few problems per page. All right, see you in the next video.